Okay, good day. This is Math 130, Intro to Statistics. I am Professor McColley, and this is Lesson 16, Finding Probabilities for Continuous Distributions. Let's get to it. Today we're going to find probabilities for normal distributed variables using technology. We're going to find a z-score given the area under the curve. We're going to transform a z-score to an x value, and we're going to find a specific data value on a normal distribution given the probability. So let's hit a quick example here and talk about what it means in context of what we learned in the last lesson. A survey indicates that the time people keep their cell phones is normally distributed with an average of 2.1 years before upgrading to a new model. 2.1 years, I think I said 2.4. This mean has a standard deviation of 0.5 years. If a cell phone user is chosen at random, what is the probability that the user will buy a new phone within the first year? All right, so in the last lesson, we talked about the standard normal curve. Let me get the right pen tool here. And it had its mean at 0, and it had a standard deviation of 1. Now, we are now talking about a new curve where its average is not at 1, but it is average is at 2.1. And so its graph is for its normal curve, and it's not a standard normal curve, is going to look something like that, with the standard deviation being at, well, if I go 1 standard deviation, 2.1 minus 0.5 is going to be 1.6, and then 2.1 plus 0.5 is going to be 2.6. And so that is going to be 1 standard deviation away on both sides. So the question is, if a cell phone user is chosen at random, what is the probability that the user will buy a phone within the next year? Now, in the last lesson, we learned that the probability is kind of the same as the cumulative area under the curve. So essentially what this question is asking is, if I came over here to exactly 1, where this is, and it's not 1 standard deviation, it's 1, where this is actually 2.1 on the x-axis, and this is our probabilities of x, we are going to essentially figure out what is this area under the curve. All right, and we can do that using that normal CDF function. So let's do that. It's second, and then the vars to bring up the distribution menu, and we're going to use the 2. We still want the lower value to be really small, and so it doesn't have to be 1 times 10 to the negative 99th, but we can make it something small. Oh, we can make it smaller than that if we wanted to, but we do want the upper bound to be 1. And here is also a change. The standard normal curve has a mean of 0 and a standard deviation of 1, but this particular problem does not. So we're going to go 2.1 there for our mean, and then we're going to go 0.5 for our standard deviation. We're going to hit paste, and we can see that it plugs all that in for us into the graphing calculator, and we get this number here. So the probability by new under a year is going to be 0.0139 or 1.39%. And again, because 2 standard deviations pretty much encompass 95% of all of the possible values, and if we split that in half into the 2 tails, 2.5%, this being only 1.9 or 39%, we would consider buying new to be unusual. All right. A survey indicates people who use Facebook spend an average of 45 minutes a day Facebook stalking with a standard deviation of 12 minutes. I made this problem up while watching my wife do Facebook. Don't tell her. Anyway, The amount of time Facebook stalking is normally distributed and represented by a random variable x. A random Facebook stalker is monitored remotely, very clandestine. It says find the probability that the Facebook stalker will stalk between 24 and 54 minutes. All right. So for one, probability between 24 and 54 minutes. Well, if I get my y equals here, we're still going to use the normal CDF, but we're going to change the parameters. We're going to change this lower bound to 24 minutes. We're going to change the upper bounds to 54 minutes. And our, let's see here, our new mean was 45 minutes, and it had a standard deviation of 12 minutes. And so if I hit enter here and a paste, and we hit the enter, we see that there's a 0.7333 chance that they will be Facebook stalking somewhere between those two values. So 0.7333 or 73.33% chance. Number two, find the probability that a Facebook stalker will stalk more than 39 minutes. So this one is going to be on the right-hand side because we want the values above that. So I'm going to say the probability that it is more than 39 minutes. Again, we'll go normal CDF. So second bars, hit 2, normal CDF. We want our lower bound to be that 39, and then the upper bound, we want as much of the curve as we can get. And remember, 2 standard deviations above, or 3.5 standard deviations above is almost all. So we don't have to go all this way, but just as a rule of thumb, 10,000 will work. If I hit enter, we see that there is a 0.6915 or 69.15% chance that they will Facebook stalk for more than 39 minutes. And number 3 says if a Facebook is monitored 200 Facebook stalkers, use part B to determine the number of those stalkers that would Facebook stalk for more than 39 minutes. Well, that's just going to be n times the probability. And in this case, n is 200, and the probability that we're talking about is 0.6915. And so when I do that multiplication, I get 138.3, or approximately 138 of the 200 people will use Facebook for more than 39 minutes. And just for reference, my wife usually spends more than 39 minutes doing Facebook. Anyway, so the next thing that we're going to do is we're going to find z-scores of a given data. And so essentially what we're trying to do is if they give us a amount of area, we can convert that into a probability on the standard normal curve, and we can calculate the z-score using a new thing, our new calculator formula called the inverse normal. It's INVNORM. And essentially what we've been doing now is given either a z-score on the normal curve or a position with a known mean and standard deviation, we have been finding areas under the curve. Well, now they're saying if you have the area, find the z-score. That's opposite. That's why it's an inverse here. So if we go to our graphing calculator and we go back to that distribution, we see the third one is this inverse normal. And so we hit 3. And so that we want the area under the curve. We want the area under the curve. If it's 70%, we're going to put in 0.7. And since we're used to this being a standard normal curve, we can do this. Now, if you have this TI-84, you can do left, center, right if you want. But I think the TI-83s only do left. So when we do the next one, we may have to fiddle with the numbers just a little bit. So I need to go down so that I can paste that in, and I hit enter. So with 70% of the area to the left, we are going to have a z-score of 0.5244. So for number one, 70% gives us a z equal to, what did I say? I already forgot, sorry. 0.5244. So just over a half a standard deviation away from the mean. Now if we want to do it to the right, 10% to the right. So we're looking, so this one was 70% to the left. The one that we're looking for now, we want this one to be 10% left to the right. 10% to the right. And so what we could do is we could calculate, if it's 10% to the right, that means there's 90% on the left. So what we could do is go to the graphing calculator and just hit second enter, but instead of 0.7, we could go 1 minus 0.1 and change this to 0.9, and that would give us a z-score of 1.282. And number three, we don't need a graphing calculator to do. And the reason that we don't need to do that is because we know that on the standard curve, if it is symmetric about the x-axis, it would be right at 0. So 50% to left would give us a z-score of 0. And let's change this just a little bit. Let's make this 10% to the right gives me a z-score equal to, what did I have? 1.2816, I think. All right, now if you wanted to, you could still do that. We could still go and we could go second enter, and we could come over to here and we could say 50% to the left, and again we get 0. So I feel vindicated in my prediction there. All right, let's move on. This also works for percentiles. Find a z-score that corresponds to someone in the 75th percentile. Well, that's fairly easy. So 75th percent gives a probability of 0.75, or an area under the curve of 0.75. So all I'm going to do is go inverse normal here, and I'm going to go second, and then I'm going to hit the delete button to insert a 0.7, have my 0.75 there, hit enter, and that z-score is going to be 0.6745. 0.6745. So the z-score for the 75th percentile is 0.6745. Transforming a z-score to an x value. To transform a standard z-score to that should be just an x value, in a given population, use the formula where x is the x value, z is the z-score, and the population mean, or mu is the population mean, and lowercase sigma is the standard deviation. Now, this may not look familiar, but it's actually a fairly easy equation, because if you remember, the z-score equation was the x value minus the mean over the standard deviation, and all we're doing here to get this one is solving for x. To get x by itself, I multiply both sides by theta. That gives me z times the standard deviation, x minus mu. If I add mu to both sides, I have have mu plus z sigma equal to x, and that's what we have. So it's fairly straightforward. This isn't a huge jump, but it says Mr. McColley records the heights of his students over the years and come up with a mean height of and with 155 centimeters with a standard deviation of 15.5 centimeters. What is the height of a student with a z-score of 1.25? Okay, well, from the last page, x equals mu times z sigma, and we know that the average height is 155. The z-score is 1.25, and the standard deviation is 15.5. That's going to give us, let's see here, let's multiply that out. So 155 times the standard deviation 1.25 times, I'm sorry, that's the z-score, times the standard deviation of 15.5, and we get, oh, what did I do wrong here? Oh, I should be adding there. That's the problem. So when you go, oh, there's no way they're 3,000 centimeters high, that's silly. We can go second answer. Oops, I don't want that. I want second entry and say, oh, I screwed up. I should have put a plus there. Hit enter. Hit enter again. And there's the number I was looking for. 174.37 centimeters. 174.37 centimeters tall. All right, moving on. Mr. McColley lets only the best students in his statistics classes. Students must take the compass placement test to be in the top 20% of test takers to get in the class. If the test takers are normally distributed and the compass test has a global mean of 75 with a standard deviation of 12.2, what score does an applicant have to receive to get into my class? Okay, so in this particular instance, what we're saying is that you have to be, in this particular instance, if we're taking our not our standard normal curve, but a normal curve, the mean is 75 right there, and then the standard deviation is 12.2. So we want to be in the 80, we want to be in the top 20%. So this is 20%, but we would say that they would be in the 80th percentile. All right. So what we can do is we can still use that inverse normal feature because we're given a percentile. So do that, do the inverse normal. And this time we want the area to be, we still want the area to be 0.8, but our mean for this particular one is 75, and our standard deviation we said was 12.2, and since we're doing it as a percentile, not the top 20%, we'll leave it as left. And so I'll come down to here to paste, hit enter again, and so on the compass test, you're going to need an 85.26 if they give partial credit. On the test, you will need either a 85.27 or an 86 if there's no partial credit. TIAL values. So if you can't get a decimal value, you have to get a whole number percentage. You're going to need the 86 to get into the class. Well, that's all I got for today, folks. So today's Marvel fun fact of the day: Doctor Strange is played by Benedict Cumberbatch, but he's also known for his voiceover work. In South Pacific, he was the Grinch. He was in Penguins of the Madagascar. He's also the Dragon Smog in the Hobbit trilogy. His voiceover work was so good that Marvel cast him as the big bag Dormammu in the Doctor Strange movie, in which he held the titular role. That's all I got. Have a good day. Bye.